This is Lab 2 Projectile Motion. Introduction. Purpose of the lab is to analyze the projectile motion of an object using experimental data and computer model data. The models that we have, so 2 computer models that will be created through GlowScript to simulate an object being projected into the air. One with only gravity acting on the system, and 2 with gravity and force, drag force acting on the system with initial conditions extracted from the experimental data, which is the other model that is analyzed in Tracker. Note that the system is the mass participating in projectile motion, and the surrounding is everything else around it, with focus on gravity and drag force. The main principle that we're looking at here in this lab is Newton's second law and the momentum principle, and that gives you the velocity and position update formula, which we use in the code. So here's the formula. So we have Newton's second law, and the momentum update formula that is used to derive the velocity update formula and the position update formula. And then here we also have the formula we used to set drag in the code. Here's the results preview. This is from the experimental data from Tracker. You see a linear line for the x versus time graph and a downward parabola for the y versus time graph. Here are all the models we used in this lab, with the first one being the experimental data from Tracker, and here is a video of what we used to extract data from. Okay, and this is what it looks like in Tracker. Okay, so from Tracker, here is the data I collected from an observation. As you can see, the graph with the time plotted against the x components of each coordinate point produces a linear line, whereas in the graph with time plotted against the y components of each coordinate point, a downward quadratic parabola is presented, which is representative of how the projectile behaves in the vertical direction. Here's the computer model that models the projectile motion with only gravity force present. Here are the most important parts of my code, with the upper left image showing the initial conditions set. I wrote both computer models as one code, and so I set B to be 0 in this model to ignore drag force. The initial position vector was extracted from Tracker, as well as the first 2 points in Tracker being used to calculate the initial velocity in the computer model. The mass was set to be 0.004 and delta t to be pretty small. On the right is the calculation or iteration loop. I defined both the force of gravity to be a vector with only y component having a value of mg, and then the force of drag, explained later, and then added them together to give you fnet, which was then used in the latter portion of the code to calculate velocity and position update data. The time is updated and the loop repeats until 0.7 seconds, which is the duration of the experimental time of projectile in motion. On the bottom is the code for the arrow that would be displayed. Here's the output of the running code. Okay, so here's the results. As seen in this slide, this is the code output, with the time versus x graph also being linear and the time versus y graph also being a downward parabola like the experimental data. All right, now we move on to building a computer model that not only takes into account gravity but also drag force. The initial conditions presented on the upper left is the same conditions from the last model, except this time B is set to be 0.002. The loop calculations on the right is also the same as the last model, except this time it will produce different results because of F air, which I titled to represent force of gravity or air resistance, is defined as negative b times the magnitude of the velocity currently squared times the unit vector of the velocity vector. Before, b was set to 0, so drag force would be negligible, but now b is a value, so drag force will be presented in the model. And at the bottom is the same code for arrows in the output. So here's the result of that code, and you can see that the x versus time graph is still linear but not as straight, and the y versus time graph being a sloping downward hill but not like a full parabola. Right now we have discussion. So comparing the data from the two, here you can see all the data from the both computer models and the experimental data, with the first row being time versus x components of position and the bottom row being time versus y components. The first row are all linear in the same direction but differ in steepness of the slope, as well as the model encompassing drag being a little curved. The bottom row all have a downward curve, but only the model with gravity and experimental data have a full downward parabola. And even then, the model with only gravity has a more narrow parabola. So looking at the difference between the 3 models, it is evident they are all different in what forces are acting on the projectile. So to answer their what if and what does it mean, what if the object was initially thrown straight up with the same initial speed as in your experiment? Would the time this object takes to reach the ground or floor or table be the same, longer, or shorter than that time that it took in your original experiment? I said it would take longer because the original was thrown at an angle, splitting the initial speed between the x and y position, but to throw it straight up means all the initial speed goes into the vertical component, which dictates the amount of time it takes to land back down, and since it will take longer to slow down and hit 0 before coming down, it results in a longer duration in the air. What does it mean? Do any of your models predict a terminal velocity? The gravity and drag model predicts the terminal velocity because at some point they equal each other, and so the net force becomes 0 and a terminal constant velocity is reached. Okay, some sources of error. One of them is the human error extracting data from tracker. Setting the point mass in each frame or setting calibration stick may not be very accurate. And 2, model assumptions. The model is not representative of real world scenarios as certain forces are ignored. And in this case, we were only focusing on gravity and drag forces. Conclusions, some takeaways. Newton's second law is very powerful and can be derived to give you the velocity and position update formula to predict motion as seen in our code. Experimental data and computer model data will always be at least slightly different, as the computer model stimulates things based on assumptions you make and are purposed to stimulate in ideal conditions or specific conditions, unlike experiments where you can't isolate other forces acting on the system. All right, thank you.